So before I introduce the next speaker, I just want to thank the organizers briefly for putting together this really unique program that I think is only possible in the modern era. So I really appreciate it. It's a very interesting list of speakers from around the world. And so now it's my honor to introduce Allan Sly, who is professor at Princeton, as well as a Sloan Fellow, a MacArthur Fellow, and more recently winner of the Loeb Prize. And he will speak to us today about spread of infections in random walkers, which is joint work with Duncan Dauvergne. Allan?
Thank you, David, and thanks both the global organizers and the Ohio organizers. It's for this very unique, very fascinating event. I'm going to be talking about sort of a pandemic inspired research. Probably at the beginning of the pandemic, you heard epidemiologists, everyone was wondering how quickly the pandemic is spreading and how supercritical it is. And one sort of model you might have heard epidemiologists talk about is the SIR model, which just stands for susceptible, infected, and removed or recovered. They basically just mean what they sound like. You have, initially everyone's susceptible to some pathogen, then and then an infection starts, and people can be infected, but that only lasts for a certain period of time, and then they're removed. Hopefully they recovered and became immune, or they met their demise. And in the most simplest sort of versions of this model, it's studied on the complete graph, and you can sort of understand what's happening by a series of differential equations. But we were interested in a more kind of dynamical version of this problem, where people are sort of living on, say, the two-dimensional plane, and they're just randomly walking around. So the movement's just modeled by a random walk. And then when an infected person bumps into a susceptible person, they pass on the infection. And then we want to know how the infection spreads. And then the infected ones sort of get cured and removed at some rate mu. And so this is sort of a simulation. The black dots are the susceptible particles, the red ones are the infected ones, and sort of this is a collection of 8 time shots, and you sort of see the infected region sort of growing over time, but leaving a sort of hollow center where, because most of the walkers or people that would have been there have been infected, but then recovered, and they're not shown. So the question we sort of wanted to understand was, if the time of the, and I mean people, but I'm probably going to default to saying particles, because we can also think of this as an interacting particle system. So if the time that they spend infected gets very big, then we want to say the infection sort of survives forever and sort of takes over the whole plane, and understand what happens there. Of course, it's possible that the infection could just die out right at the beginning. And actually, the first time I did the simulations for this slide, that's exactly what happened. And I plotted the simulations, and it was just all black dots everywhere, and nothing happened. So this is sort of, which doesn't look very interesting. So this is the sort of rerun simulations. An alternative, sort of simpler model that people had looked at more in the past is, what if you don't have the recovery? So we just term this as the SI model, and now we should just have a growing ball of infected particles, and so the region of infected particles should just get bigger and bigger, as you sort of see. Just to set up the problem, we're imagining that initially everything's kind of in equilibrium, and the sort of natural initial condition would be to have a Poisson number of people at each vertex of the graph. This would just be the stationary distribution for them all doing independent walks. And then at time 0, we introduce a single infection at the origin, and then see what happens. And another thing you could say as well, they're all doing random walks, but maybe the speed of the infected particles, maybe they're walking around slower because they're infected. So we could have different speeds for the susceptible and infected particles. Okay, and so this model has sort of various results in the special case where the speeds are the same. So going back about 15 years, Kest and Sidorevicius showed that if you look at the set of infected particles, that its diameter grows linearly in time. So it sort of spreads out at some sort of linear rate. And so you should keep in mind that that means that the area that's infected is growing much faster than the individual random walks are moving. So in time t, the random walkers will move about distance square root of t, but the infection process will move like a constant times t. And you could ask more than just sort of what's the size of it. You could ask sort of what does the shape look like? It sort of looks like a ball, although it's on this scale it still looks a bit rough. And so a few years later, they were able to show a more refined result, which was that there's some deterministic shape U that's symmetric and convex, and that essentially the location of the infected particles is like a scaled version of this set U. So it's like T times U. So in particular, everything within 1 minus epsilon times T times U is infected, and everything outside of 1 plus epsilon times T times U is still susceptible. And the basic way, at least for the first theorem here, that they, the reason why, well, actually both the proof and the reason why it's true is that if you have some local region and there's some the infection is there, and there's a reasonable number of other random walkers there, the density isn't too low, then pretty soon a few of the other ones that are susceptible will get infected. Some of them will move to the left, some will move to the right, some will move up, some will move down. There's sort of a drift, an outward drift of infections from any infected region, as long as the density isn't too small. And so, if you consider the sort of front of the infection, the location where the infected particles meet the susceptible ones, as long as this isn't spending too much time in sort of very sparse regions where there aren't too many people, then it should sort of have an outward drift and on average grow linearly. So the sort of challenge for Kest and Sidorevicius was to show that basically the front can't spend too much time in sort of sparse areas. And the proof of this, they could do essentially without thinking about how the evolution of the process, the infection process at all, because if the speeds of the two types are the same, then if you just look at the random walkers without their labels, then they're just doing independent random walks. And so you can study the sort of locations without respect to thinking about who's infected and who's not. And the Poisson distribution is the equilibrium one. So in any sort of spatial region that's sort of reasonably large, the probability that you have sort of a lot smaller number of particles than you expect should be very small. So sparse regions are rare. Also, like spatially, they're sort of independent, but in time, there's sort of dependencies. So if one region is sparse at one time, then it's more likely to be sparse at a later time. But using a sort of multi-scale argument, they showed that the sparsities sort of dissipate reasonably quickly. And so essentially the regions where there aren't too many particles are kind of basically rare and independent of each other. And so essentially, however the front of the infection process moved, it couldn't spend too much time going through these sparse regions. And so it must have a good drift everywhere. And so it expands pretty at a linear rate. But this used in a really fundamental way the fact that the speeds were the same for the two types of particles, and it sort of completely breaks down if you don't know that. So when the speeds were different, this infected particles, I wrote type B. Sometimes they're referred to as type A and type B. They showed grows at least like T over log T, so not quite linear. And this is because the dependent of the infection process and the location of the walkers is dependent in some kind of potentially complicated way. It also doesn't have any kind of nice monotonicity properties, because you could imagine if you might think that if I add in more people, then that will just speed up the infection process. But at least in a pointwise sense, this isn't necessarily true, because if I add in someone else, they might get infected and then infect someone else earlier, which then means that that next person is, at a different location and then fails to infect someone else, a third person, at a later time. So, and without this sort of monotonicity, a lot of the tools that have been developed don't apply. On the other hand, it seems like really, really obvious from the simulations that it should just be growing nicely. There shouldn't be really any problems, and you should have a sort of nice linear growth rate. And the fact that it's growing linearly, which is much faster than the random walks are moving, means that the sort of front of the infected region should keep encountering new independent particles that haven't been infected yet. And so the process should sort of keep revealing new sort of random particles. And so what I want to tell you about is basically a way in which to make this sort of heuristic into a proof. But first of all, I want to, to do that, I want to tell you about a sort of slightly different model involving particles that maybe more of you will have heard of. This is called diffusion-limited aggregation. And essentially, this is a bit like the model I've been talking about, except the speed of the infected ones is 0. And so we just add in one susceptible particle at a time. It does a random walk until it hits the other infected ones, and then it just freezes there and stops. And so this is sort of an aggregate or shape that's sort of growing one particle at a time. And if you do this, you get these very nice simulations. So the top right picture is a simulation of this DLA process, and you get these sort of fractal pictures. They look very tree-like. There's a lot of space sort of left out there. And these are meant to be models for sort of real phenomena. So in the lower right picture is an experiment of electrodeposition in a copper sulfate solution. Okay, this is a notoriously difficult problem, and almost, many very simple questions you might ask are not known. So you might look at the picture and say, well, the fractal dimension has to be less than 2. That's not known. You might say that, the limit of it is not just sort of a, if you add in n particles, you must get something that has diameter that's bigger than a constant times square root n. Even that's not known. So I'm not going to tell you anything new about this this problem. It's sort of, I don't know, I find it very humbling every time I try and think about this one. But but closer to the problem I told you at the beginning would be sort of the multi-particle version of DLA, where rather than adding in one particle at a time, you have sort of a sea of particles with some density that they're each doing independent random walks until they run into the aggregate and get frozen there. Now, if you imagine that you start from sort of some very low density of particles initially, then this should look like the DLA process a lot. So here's a simulation where the initial density was, I think, 0.3. And I don't know what the resolution is going to look like on your screens, but if you look at the center of it that's in black, it sort of looks fairly tree-like, a bit like the DLA process that we had on the previous slide. But on the sort of larger scale, it's starting to look pretty regular, like almost like a sort of smooth diamond kind of shape. And this is certainly what's expected when we have a high density of particles, but that's not known at any density. Sidrovicius and Stauffer showed that you get a sort of linear rate of growth in a sort of slight variant of this model when the density is sort of very close to 1. And I had a different proof that showed that when the density is at least 5/6, it grows linearly. And I want to tell you a little bit about both of these arguments because they'll both be useful for studying ultimately the SIR model. Okay, so you might wonder if at low densities it behaves more like DLA. But actually the conjecture is that there's no phase transition in dimensions 2 and higher. It just, if we look on a big enough scale, eventually there'll be some sort of limiting shape that should emerge. And the fact that the pictures initially look like DLA, that's just telling us that we haven't been running the simulation for long enough. Okay, so there's no phase transition except in dimension 1. Now dimension 1, things are much simpler because the sort of aggregate, the frozen infected particles are just a line segment. So all you can really ask about is the length of that, and I'll call that xt. And Kessler and Sidrovicius showed that it grows like square root of t when lambda is less than 1, basically because there aren't enough particles around for it to grow any faster than that. Conversely, when lambda is greater than 1, I showed that it sort of grows at a linear rate with some asymptotic speed. So this is in one dimension, but there's actually a way of coupling this with the higher dimensional problem, so that by looking at sort of the speed of the rightmost particle of that aggregate and how that grows, and you can show that that grows at least as fast in higher dimensions as it does in one dimension. And actually you can do a bit better. So in dimension 2, for instance, you can show that you get a linear speed when lambda is bigger than 5/6. So lambda, the sort of density of particles you start off with. You can also ask about the critical value lambda equals 1, and there the speed is t to the 2/3, and one can this is joint work with Dor Elmboim and Danny Nam, and you can sort of describe the scaling limit as the integral of some quite non-trivial diffusion process that's a power of a Bessel process. But I won't get into that. Okay, so I just want to make one sort of key observation from the proof of this, which is essentially what we can think about in terms of if we condition on, say, what the infected particles have done up to a particular time. So in the one-dimensional case, this is just about knowing what the aggregate has done from time 0 up to time t. And then I could ask, well, if I want to know when it grows, I need to know how many particles there are just to the right of the aggregate. So what's the distribution of that? Well, what does it take for a particle to be just to the right of the aggregate? That means that their past trajectory has to have missed the aggregate, so that they didn't get infected before that time. And initially I said that the distribution of the particles was Poisson with mean lambda. But we could think of the initial condition as not just a Poisson process on initial locations, but a Poisson process on initial locations and future trajectories. So this is a Poisson process on a more abstract sort of path space. And so, and the paths that lead you to this point at this time are just the ones that avoided the aggregate before that point. So conditionally, the number of points there is Poisson. And we can even write out the probability or the density of it. It's just lambda times the probability of a time-reversed version of the aggregate being greater than or equal to a random walk. And then the sort of asymptotic, the speed or the infinitesimal jump rate of the process is just given by half of that. And you can sort of analyze this speed and show that there's sort of a mean reverting property, that it doesn't get too slow. And if it gets too slow, it will tend to sort of speed up again. Okay, but the main sort of takeaway I want from this is that if you just condition on sort of revealing what the infected particles are doing, what the remainder of the process still looks Poisson, but with a sort of modified value of the density. The second approach was by Sivakoff and Stauffer, and they considered multiparticle DLA with a slight variant where your own particles are doing an exclusion process, which means that there's only one person allowed on each vertex at a time. And so if they try and jump onto a vertex where there's already someone there, then they just don't make that jump. And they looked at this problem when the density was really close to 1, something like 1 minus epsilon. So almost everything is occupied, and there's just occasional empty holes where you don't see people. And what they showed was that the aggregate or the infected particles will be sort of growing over time. But every so often they'll encounter one of these holes where there's no one there. And what they show is that then the aggregate will have a good chance of sort of surrounding it and then sort of keeping on moving after that. So these holes get sort of, so the black region is supposed to be the aggregate, and it sort of surrounds the little holes that it encounters. But then occasionally it will encounter a group of holes all at the same time. So it may need a bigger sort of radius to be able to surround those. But those are rare, and so they show that you can sort of keep going with this process in a sort of multi-scale way. And they did it by introducing a process that with the kind of unwieldy name of first passage percolation in a hostile environment. And this is, which is essentially a competing growth process. You have a red process and a blue process. The red one just spreads to its neighbors at rate 1. The blue process initially starts off with seeds all over the plane, at each site with probability epsilon. But they don't start growing initially. They only start growing when the red process runs into them. And then when the red process runs into them, then they start growing at some rate theta less than 1. So the red process starts growing, then it runs into the blue one. This activates this blue one, so it starts growing, but the red one is growing faster. And so there's a good chance that the red process will surround the blue process. And what they showed was that if the initial density of blue seeds was small enough, then essentially almost everything will end up being red. It will have a sort of infinite component. At least with positive probability. There is a chance that the initial red seed was just all surrounded by blue ones, and then it can't grow. So we looked at sort of a simplified variant of this, and basically where the sort of essentially the speed of spreading became deterministic. So the blue seeds jump at rate, move after timing exactly 1. The red ones expand to their neighbors after time at most delta. And so with this sort of determinant, so the red one's moving a lot faster than the blue one now. And so if I draw a sort of circle around each blue seed, basically if the red process comes along, reaches a blue seed, because it's moving faster, it will sort of surround it, and everything outside of this circle around it will become red. It will, because the red process is moving faster. So that works fine when it's just encountering a single blue one at a time. But sometimes it will encounter pairs of them. And then we might need to make a sort of bigger buffer zone around those ones to ensure that the red process sort of can move quickly enough to surround them. But sometimes those sort of second level balls might be too close to each other as well, so we might need to put those in an even bigger ball. So there's some sort of description of this in sort of surrounding problematic areas in bigger and bigger balls, but such that the density of these balls is sort of bounded by say 2 times epsilon, and so that there's a good chance that the initial red one is outside of all of these balls, and it will infect everything that's outside of the union of the balls. And so you can so how does this relate to the SI and the SIR model? So I want to tell you how we can sort of put those ideas together. And the idea will be to try and maintain some sort of independence of different spatially disjoint regions, sort of independent randomness. And the way we'll do that is by sort of only revealing what's happening in a sort of small window in the plane. So we'll first divide the plane into boxes of length L, where L is just some constant. And then the first box will be shaded red. And every time an infected particle enters a new box, that one will get shaded red as well. But if a box has been next to a shaded box for time more than L squared, then we'll shade that one too, but I'll shade it in blue instead. And what we reveal is all the particles that have been in a shaded box at some point in time. So the process will grow something like this. When the infected particle enters a new box, it sort of, the shaded region expands to it. And then these 2 boxes were next to the central box for enough time. No infected particle entered them, but we're still going to sort of shade them as if the time has been at least L squared. Okay, and we only reveal particles that have been in a box at a time that it's been shaded. So, And in doing so, we can just sort of we can understand sort of well the conditional distribution of what's happening outside of those boxes. Okay, and so basically what we want to do is sort of say each time we shade a new box and reveal what's inside it, we have to decide what particles get revealed there, and we're going to make those decisions at the very beginning of the process. So for each box, I'll have an independent Poisson process in the box, and this will tell us what should appear when the box gets shaded. So this box, this one just got shaded. So we look to the right and see, okay, there was one particle here, so we put a particle in the corresponding spot. And we keep going with this. Now, 2 more boxes got shaded, and we added the corresponding particles, and we can sort of keep going with this. And so the point of this procedure is that what we're discovering was something that we sort of just created at the beginning. Each box was independent, so this gives us sort of a degree of spatial independence of the process. But what I've described so far is not quite right, because we only want particles whose past trajectory has avoided the shaded region. So what we should really do is sort of only take some of the, to take a lower density of Poisson process when we discover a new block. So imagine now here on the x-axis is space, on the y-axis is time, and at time t, in this box, it becomes shaded, and we've got to decide what to do. So initially, we generated a Poisson process, but we only want particles whose trajectories have avoided the shaded region. So I'll sort of draw the corresponding shaded region in there. And we can just draw independent past trajectories for them. And we want the ones that avoided the shaded region. So we just delete the ones that went through the shaded region, and keep the ones who didn't. And these are the points that we add into the process. And then we sort of keep running it from then on in. So this sort of tells us the way in which the dependence on the past of the process affects the new particles that we discover when we discover a new region. So it's not independent. So you might worry that how is this helping us if we keep discovering new areas but they're not independent of the past? Well, we can sort of show that there's a sort of certain minimum density of particles that we should be discovering. So the idea will be, okay, we want to couple this to the first passage percolation in a hostile environment process. And I need to tell you what a blue seed is. And I'm going to tell you the opposite of that. What is sort of something that's not a good seed, something like a good block, essentially. And a good block will be one where if an infected particle enters it, and when it gets shaded, then there'll be lots of particles, then we'll discover lots of particles there. Lots of those will quickly get infected and quickly spread the infection to all the neighboring blocks in time somewhat smaller than, in time about delta L squared. But the problem is the shaded region around this block is random. But there's sort of a worst case shaded region, and this is because the shaded region grows sort of one block every L squared time. So if we move L squared blocks away from our block B, then that block can have only been shaded by time k times L squared. So the maximal shaded region is some sort of essentially, well, the complement of a pyramid shape. And so the particles that we definitely keep are ones whose past trajectories stay within some pyramid. And at least for ones towards the center of the box, you can show that these walks have a positive probability of doing that. So typically we will get order L squared number of particles when we reveal this block. And these particles, and that's enough that, you know, a lot of them will quickly get infected and quickly spread the infection to neighboring blocks. And so, and at least by taking L large enough, we can make the probability of that not happening and being a blue seed as small as we want. With this process, there's also going to be enough infected particles around all the time to quickly infect any nearby susceptible particles that don't get infected straight away. So the sort of final result for the SI model is that after time t, with high probability, everything in a ball of radius at constant times t will be infected. Now this is with probability tending to 1. The first passage percolation in a hostile environment fails with a positive probability. And so to get it to be with probability 1, we should take the size of the block to infinity. So we sort of get around this by taking large blocks initially, and then sort of smaller blocks sort of further out. And this way we get the speed, the probability is close to 1, but the asymptotic speed doesn't depend on the probability that we want. But a sort of all this really says is that there's a certain speed at which it grows. We don't know something like a shape theorem, that there's a limiting shape that it occupies. And so getting back to the original process that I talked about on the first slide, the SIR model, the same approach holds in this case. So we can sort of couple the infected regions with the first passage percolation in a hostile environment process and show that it's growing at a linear rate. Because the infections die out so quickly, the width of the infected sort of boundary is only typically of a constant order. So it's really, we really have sort of like a one-dimensional boundary here that sort of, so you have a linear-sized hole in the middle, just a boundary of a constant width, and then all susceptible particles outside of it. And so what we show is that with probability close to 1, and you can make it as close as you want to 1 at the expense of letting the sort of infected particles or the sort of recovery rate being sufficiently small, then it goes on forever. And once the wave of infections has passed through some area, after a very short time after that, just like a large constant time, you'll typically never again see any infected particles there. And for every location, you won't see any more infected particles after time. The right thing should be about log t. I think we get like log to the log t time. Okay, so really in the middle here, you see no infected particles at all. And so what do you see in the middle? Well, you get sort of what we kind of felt like calling a sort of herd immunity regime, where there's sort of a low but positive density of susceptible particles. These are the ones that essentially manage to socially distance their way through the wave of infections, dodging any of the infected particles. The then the wave of infections passes through, and then after that, pretty soon there's no more infected particles around. So each particle has sort of about a constant probability of not being infected, and then is left in this sort of sparse region of where there's still some susceptible particles. It's a positive density, but the density is low enough that it's not enough to be able to sustain the sort of infection process after that. And okay, and maybe I'll leave it at that. Thanks for listening.
Great, thank you, Allan. Let's maybe thank Allan. And does anybody have questions? Maybe I'll ask one. Can you go back just one slide? Can you say anything about the density of these particles in the herd immunity case, the particles that don't ever become infected?
So it should depend on mu, the sort of the rate at which, like the length of the infection time, and I think presumably it should be like exponentially small in mu. I think our bound is like much worse than that. It was kind of a bit tricky doing this simulation because you want to make the infection sort of infectious enough that it doesn't just die out, but not too infectious that you leave a reasonable number of particles in the middle here. So it sort of took some fine tuning to get a picture that sort of matched the theorem, which maybe says that the theorem only really applies on sort of larger scale things, and the density you'll get is actually fairly small. I mean, this is sort of also, this picture doesn't look sort of typical in terms of how you would expect it, because like at least in the top right hand side it looks concave rather than convex, and surely there should be some sort of limiting shape, and it's certainly not going to be concave. Yeah, again, that's sort of just not running the simulations on a big enough system in a sense. Yeah, so we could say that sort of in any sort of medium-sized local neighborhood, the particles you see there will at least stochastically dominate some Poisson process. But we don't know much about the densities.
Thanks. Any other questions?
I think you earlier in your talk, maybe you were talking about the SI model, and it seemed like there was like linear growth, but like sort of in a strong sense, like there's actually a convex shape. Is that right?
That's what we expect, and so in the case where the speeds of the two types are the same, then that's known. And I think one of the most interesting open problems is establishing that there is some limiting shape. It must be convex if it exists, but yeah, we don't know how to prove that. In the case of the sort of equal speeds, Keston and Sivakoff essentially were able to use some kind of approximate superadditive ergodic theorem type result, but that relied quite strongly on sort of monotonicity properties, which are morally still true in the general case, but only approximately, and so we don't know how to.
And in that case, where they're equal, and it's known that there is a limit shape there, but is anything known about the limit shape, or is it like it's
No.
like first passage percolation? where
Right,
we don't know
yeah, I mean,
anything?
it's probably even less than we know about limit shapes in first passage percolation. Yeah, just I think only convexity.
Thanks.
If there are no more questions, maybe we'll thank Allan again. That was a great talk. Thanks so much, Allan.
Oh, thanks everyone.